Hello again. This is Math 2232 coming to you from the College of DuPage, and the title of this lecture is The Integral Test. As always, please be attentive while watching this video. By way of introduction, we're going to discuss a little bit more about the harmonic series. Now, and we'll end up coming up with another proof that this diverges. But the reason we're going over the proof is that it is instructive, and eventually we'll end up with a result that has very broad applications well beyond the harmonic series. So let's start off by looking at an apparently unrelated problem. Let's start out by asking, what is the area under the curve f of x equal 1 over x on the interval from 1 to infinity? Now we know that from the lectures that we had on improper integrals earlier, and that is that the integral from 1 to infinity of 1 over x dx diverged, and we called it infinity. Yes, and divergent is the same term we're using here, but this time with series. So just how does this help us prove the harmonic series diverges? Well, recall that we can always estimate the area by breaking up the interval into segments and then sketching in rectangles and using the sum of the area of all the rectangles as the estimate of the actual area. Let's do that for this problem as well and see what we get. So we're going to break the interval into pieces where everything is of length 1, of width 1. And we'll take the function value at the left endpoint of the rectangle as the height of the rectangle. This is the left. So this one will be 1. This one will be 1/2. This one will be 1/3, and so on and so forth. So the image shows what we're doing. And notice that we're taking the function f evaluated at x sub n is equal to a sub n. So you see we're really picking these values carefully. So the area is approximately equal to the sum of these rectangles. Since the bottom is always 1, we're always multiplying by 1, so it's just going to be 1 plus 1/2 plus 1/3 plus so on and so forth, which is actually exactly the harmonic series. Now this area was approximately this rectangles, and you notice that the rectangles overestimate this area. So the area under the curve is approximately the same as the harmonic series, but this was an overestimate of the integral, which we know is infinity. That means that this is bigger than or equal to infinity. That means it equals to infinity, and so the harmonic series is in fact divergent. So this is another proof that the harmonic series is divergent. So we've managed to relate a series to an improper integral that we can compute. And it turns out that the improper integral and the series have exactly the same convergence in this case. Not the same values, but the same convergence. Let's see if this will also be true for a series that converges. So when discussing the divergence test, and recall that the divergence test was in an earlier lecture, and that was the first of many powerful convergence tests we will study. The integral test is the second. But back in those days, we made the claim that this, the summation n equal 1 to infinity 1 over n squared, converges. Well, let's see what happens if we try to do a similar technique with this. It'll be more involved, but again, it will give us insights. So let's try to see, what do we know about the area under this curve? F of x is equal to 1 over x squared on the interval from 1 to infinity. Again, we know from the earlier studies that we did, this integral can be evaluated, and this integral in fact is equal to 1. So the integral converges. But once again, we're going to try to estimate the area under this curve. We'll do this in almost an identical manner, not exactly, but almost identical as the earlier discussion, with the exception that instead of using the left endpoints for the heights of our rectangles, we'll use the right endpoints. Here is a sketch of that case. Now the area is an underestimate, or excuse me, the rectangles are an underestimate of the area. But in this case, the area is approximately equal to This is 1 over 2 squared plus 1 over 3 squared. Again, we're taking units here. So that makes the calculation very easy. So you see that the area is approximately 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, 1 over 5 squared, and so on and so forth. And so what we know then is we can do the following. We can say, well, this, the summation of all the squares, which was approximately that, is an area estimation. But the area estimation is less than the value of the integral. So this is less than 1 plus the value of the integral, and that's actually twice the integral, so this is 2. So you see what we do is we get an inequality here. And putting this all together, we can see that this, the summation from n equal 1 to infinity of 1 over n squared has to be less than 2. Now, when we were studying the harmonic series, that's all we needed to say, that the series was convergent. But with this series, however, that's not quite enough. For example, what happens if this added up to something that was less than 2, say minus infinity? Then it would diverge, so we have more work to do. So let's notice first that all the series terms are positive. That's important. And in fact, it's going to be increasing, because if I add something positive to an existing sum by adding one more term, Sn is less than Sn plus 1. So these are increasing. And we know that they're bounded. So an increasing bounded sequence converges. We know that. So what we can say is this is increasing and it's a bounded sequence. And so we know that a bounded monotone sequence was guaranteed to be convergent. This means that the sequence of partial serves is a convergent sequence. Well, okay, that means that it must also be that the series must also be convergent. And this is a new result for all of us. So once again, we were able to relate a series to an improper integral that we could compute. And the series and the integral had the same convergence. Now, we went through a fair amount of work in both of these examples to determine the convergence of the two series, but we don't have to do this every time, and the ideas in these two examples are summarized in the following test, which also is a theorem which we will prove later in this lecture. This is the integral test, and there's always important conditions. Suppose that f is continuous, positive, and decreasing function on the integral from k to infinity, and that f evaluated at n is a sub n. Then, if the integral from k to infinity f of x dx is convergent, then so is the summation from n equal k to infinity of a sub n. Moreover, if the integral from k to infinity of f of x dx is divergent, then so is the sum from n equal k to infinity of a sub n. Said another way, which is the way I like to say it, is that the indefinite integral, that the improper integral and the infinite series under these conditions converge and diverge together, but not to the same number. So there are some more things we should note about this, and we'll look at the proof later. First, the lower limit on the improper integral must be the same as the value that starts the series. So this k must match with this k. Second, the function doesn't actually need to be decreasing and positive everywhere in the interval. Remember that I said it's all about the tail, so all that's really required is that eventually the function is decreasing and positive. In other words, it is okay if the function, and hence the series terms, increase or are negative for a while. In fact, it could be a long while, but eventually the function, series terms, must decrease and be positive for all terms. And to see why this is true, let's suppose the series increases or are negative in this range, then what we can do is we can break this into pieces. And it's all about the tail, so this is the one that really matters as far as the convergence, and this is just some finite numerical noise in the problem, at least if we're talking about determining whether it converges or not. Okay, and this pretty much says what I said. And a similarity can be made for the improper integral as well. Now, the requirement in the test that the functions be decreasing positive in the range is required for the proof, however, but in practice, we only need to make sure it is actually decreasing in positive function in series for the tail. There's one more very important point to be made about the test. The test does not give the value of the series. You see, they will converge and diverge together, the improper integral and the infinite series, but we don't have the same values. It will only give the convergence and divergence of the series. That's it. For example, we knew that this one was just less than 2, but in fact, it is known that if you actually sum this, summation from 1 to infinity of 1 over n squared, this is pi squared over 6, which is less than 2. And the great Euler proved this result. But you see, this is not the same as what that integral was. Euler proved this result of pi squared over 6, and with new tools that we will be coming soon in this course, we will prove this result. So much to look forward to. Let's do some problems here. And again, I'm highlighting these because these are things you should either do now or as you study, go back and make sure you understand. Determine if the following series is convergent or divergent. This is a summation from n equal 2 to infinity 1 over n ln n, natural logarithm of n. And we start at 2 because the ln of 1 would be 0. We'd have a 0 in the denominator. Okay, in this case, we simply just, using the integral test, we just need to talk about the function f of x is equal to 1 over x, ln x. Now this function is clearly positive, and if we make x larger, the denominator gets larger, so it's also decreasing. You see, you do have to verify that it does satisfy the preconditions of the theorem. But therefore, all we need to do is compute the convergence of the integral. Well, let's compute this integral. So the improper integral from 2 to infinity of 1 over x ln x dx is a limit as t tends to infinity of this. We do a u substitution, u equal ln x. And when we do the integral, and make sure you follow this, but this is the limit as t tends to infinity of the natural logarithm of x at t and 2. So whenever we put these values in and take the limit, and even though the logarithm grows very slowly, and the logarithm of the logarithm grows very slowly, we see that this is infinity. And so this integral is divergent, and so by the integral test, the series is also divergent. Let's study this one. Determine if the following series is convergent or divergent. And again, this is a good example for you to do. The summation from n equals 0 to infinity of n e to the minus n squared. Okay, again, this is continuous. It is f of x equal x e to the minus x squared is continuous. It is decreasing. Actually, it's not decreasing forever, but it is only increasing on the interval from 0 to 1 over the square root of 2. And so for the tail, from 1 over the square root of 2 to infinity, it is decreasing. You see this function goes up for a little while, then it goes down. So it will eventually be decreasing, and that's all we need. So what we're going to do is we're going to compute the integral. This time, so this is the improper integral from 0 to infinity x e to the minus x squared. We'll use a substitution u equal minus x squared, and we compute this, and we get that this integral is 1/2. Now that doesn't mean that the series sums to 1/2, but it does tell us that the integral is convergent, and by the integral test, that means the series must also converge by the integral test. And if we generalize this, remember that we computed those p integrals earlier. And we found out that the improper integrals converged if p was bigger than 1 and diverged if p was less than or equal to 1. This was back in the chapter on improper integrals. And so here, if k is greater than 0, then the sum from n equal k to infinity, again, it's all about the tail of 1 over n raised to the p power, converges if p is greater than 1 and diverges if p is less than or equal to 1. A very powerful result. And in fact, we can use that powerful result to quickly determine things. For example, here's a problem. I give you two problems here, actually. Determine if the following series are convergent or divergent. So the first one, since p is 7 bigger than 1, that will be convergent. And since p is 1/2, this will be divergent. It is important to note before leaving this section, I'm stressing it again, that in order to use the integral test, the preconditions must be met. The series terms must eventually be decreasing and positive. It's all about the tail. If they are not, the test doesn't work. You have to do something else. Maybe. Also remember that the series only tests the convergence of a series and does not give the value of the series. Okay, so let's talk about the proof. And the proof's going to look very similar. We're just doing things nicely. So we start with this, this series, and we're starting at 1 because starting at k is all about the tail. We also could have formally done just an index shift to n equal k. But either way, we'll do it for n equal 1, and that will be sufficient. And also note that while we allow for the first few terms to increase or be negative when working the problem, the proof doesn't require all the terms to be positive. It's really that, but we're just going to do that, and this is without loss of generality. Okay, so we again take f of 2 to be a2, f of 3 to be a3, and so on and so forth, and we draw this curve. We know it's decreasing, so it looks something like this. We approximate the area by the finite sum, and so we know that since this is an underestimate, that we're bounded above by this. Now suppose that this integral is convergent, and so this must have a finite value. And so what we can say is that the sum of the series is less than or equal to the first few terms plus this integral, and we'll call that m. Well, okay, so that told us that this is bounded above by m, and also by the conditions of the function. This is increasing, so it is convergent. So the first part of the theorem is proven. The second part is easier. This time we're going to overestimate the area by defining the other endpoint. We know this is a decreasing function, and here what we find out is that that the area, the partial sum, is bigger than this part of the integral. So suppose this is divergent, then that means that this will also diverge. So you see, we've really proven the entire theorem. Well, I guess we really should finish it here. So as n goes to infinity, this goes to infinity, and that tells us that s sub n goes to infinity. And that's the end of the proof. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and each other. We're in this together. May God bless you all.